अस्सलाम वालेकुम स्टूडेंट। आज की इस वीडियो के अंदर हम बात करेंगे फाइनाइट ऑटोमेटा की, और उसके अंदर भी जो एक स्पेशल केस है डिटर्मिनिस्टिक फाइनाइट ऑटोमेटा, उसकी हम डिस्कशन करेंगे। तो पहले हम डिस्कस करते हैं कि व्हाट इज फाइनाइट ऑटोमेटा। व्हाट इज फाइनाइट ऑटोमेटा? फाइनाइट ऑटोमेटा is actually another way of defining the languages. It represents an abstract machine that is used to define a regular language. The limitation that we have with the finite automata is that it answers either yes or no. So there is no midway. And so that's why it also acts as a language acceptor. We have already discussed regular expressions, and there is a relationship between finite automata and regular expression. And that relationship is that the language which can be represented or generated through a regular expression can also be represented or generated through finite automata. It means that every regular expression is represented by some finite automata, and every finite automata has an equivalent regular expression. There are basically three components of the finite automata. The one is the state. State can be have a dedicated start state, set of final states, and there are intermediate states. While the alphabets that we have already discussed in the regular expression, these are the language defining symbol. In case of finite automata, these alphabets are input letters, and there is a transition that is actually a path for each input that determines what would be the next state on a given input from the current state. Now, we talk about, there are actually two classes of finite automata. One is non-deterministic finite automata and deterministic finite automata. In this video, we will discuss only the deterministic finite automata. For deterministic, by meaning, it means that we uh, can predetermine the next state on the current input. So in each input, there is one and only one state to which the machine can move from the current state. So there is no other way. If, for example, we can just define, for example, if you are in the state Q and there is an input A, and then it is predetermined that what would be the next state. Secondly, it does not accept the null moves, missing transition. And if we have to deal with the missing transitions, then we have to incorporate a dead state. And this dead state is required to accommodate all the missing transitions. Now, the question is, what is a dead state? A dead state is a special type of intermediate or non-final states. Once a machine enters into a dead state, and there is no way to leave it, as it does not have outgoing transitions. So if there is no outgoing transition, it means we cannot move out of the state. We can only come into the state. So once we are inside the state, we will remain within that state, and there is no way that we can move to the final or the accepting state. That's why the state is called a dead state. Now we talk about the formal definition of deterministic finite automata, or DFA. A deterministic finite automata is a five-tuple notion that consists of a finite set of states, and these states are represented by Q. So this Q is a finite set that consists of states like Q naught, Q1, Q2 up to Qn. Then a finite set of input symbols, alphabets, and it is denoted by sigma. Although the symbol sigma is same as we have defined in case of regular expression, but in this case, these are input symbols. Input symbol means the input that will be given to the automata to recognize it or accept it. That input uh, string will actually be based on these input symbols. And there is a transition function. A transition function means uh, it's a function because it takes two arguments. One is the state, other one is the alphabet, and determine what could be the next state. For example, we are in some state Q, and from the state Q we have uh, an input A, then it would determine that the next state would be P. So now, as we have mentioned in this transition function, so delta is the symbol that defines the transition function. This function takes two arguments, Q and A, and gives as the output the next state. So every transition that is provided in the DFA has an equivalent transition function. It is also mapping between Q times sigma. It means for every state, there are at most as many transitions as the number of input symbols are in the sigma. Secondly, the last one, uh, second last one is that it has a dedicated start state, that is Q naught, and Q naught always belongs to finite set of state, that is Q, and a final states that is also a finite in count. It may be one or maybe more than one in any DFA. Now we understand it with some example. There is a language L, that is there is a string W such that W is of the form X 0 1 Y for some strings X and Y consisting of zeros and ones only. The first thing that we need to do is that determine that how many states we can have for this particular language. One thing that we can notice that in this particular language, there is a substring 0 1 which acts as a constant. So 0 1 is the minimum string that will appear in this language, and for X and Y, it is actually consisting of zeros and ones only. So there may be any sequence of zeros and ones, but 0 1 as a constant will appear as a substring in all the words that are generated or that are the part of this language. So first determine what the basic ingredients we need. There is sigma, that in case sigma is 0 and 1, because 0 1 as a constant here, and again we notice that X and Y consist of zeros and ones only. So since there are 0 1 is the minimum strings, so we need at least 3 states to generate this 0 1. And now for X and Y, we will make some modification for the transition on the existing states. Designated start state Q naught, and F is the final set of state, and in case Q2 would be the final state, and a transition function that will determine the transition. So first of all, there is a state Q naught. Okay, these are some words that possible words that can be generated from this language: 0 1, 101, 001, 101, 110, 11. But in all cases, we can notice that 01 always appear in the string, like this, and this, and so on. So now, first we draw the state Q naught, and then we need a state Q1. So now there would be a transition from Q naught to Q1 because the substring starts with the letter 0. So there is a transition from Q naught to Q1 that will that is on the basis of the input 0. So there is a transition function, equivalent transition function we can have like this. For example, the transition function says that from the state Q naught on the input 0, we will move to the state Q1. Now, next we need one more transition for the input 1. So we have to draw one more state, that is Q2, and then there is a transition for 1. Now, Q2, as it is double circuit, so it is the final state, and this transition actually is defined as like from the state transition function says that from the state Q1 on input 1, we will move to the state Q2, and Q2 is our final state. Now, for the state Q naught, this is the start state, and after the Q naught, we have a transition to the state Q1, that is 0. Now, there may be so many ones or a single one before this 0, as in this case, 1 or 1 or 2, 1. So for this, we have to make a loop on the Q naught. So this will handle if the string starts with 1. So this loop is actually indicates a closure. Closure means that this loop may execute or may not execute. So may not means that we will skip this loop and we will start with the 0. Okay. Secondly, there may be so many zeros before this one actually. So 1 0 is mandatory to make it 0 1. So for the second 0, we have a loop and this Q1 state. So this is again an optional case. The loop may or may not execute. It always executes a closure operation. So closure means if it doesn't execute, it means an epsilon is generated. And if it executes, then the number of time it will execute, it will determine the number of input alphabets that will be transit through this loop. Then we have, so far, we have completed the X and the 0, 1 part. For the Y part, once the 0, 1 is transit or is recognized, and after the 0, 1, we can have any sequence of 0 and 1. So we will have a loop at this final state that is 0 and 1. So this is the final DFA that will recognize all the words having the form X, 0, 1 and Y. For every DFA, we have a transition table. So let's talk about what is transition table. A transition table is a tabular representation of the transition function, where the rows of the table corresponds to the states and the columns corresponds to the input. So here, for this particular DFA, we have this transition table. So as in the rows, we have states Q0, Q1, Q2, and in the columns, we have input symbols. So we have only two input symbols, that is 0 and 1. So this is the transition function. The intersection point is actually the output of the transition function, while the corresponding column and rows entries are the input or the parameters for this transition function. So for the transition function from state Q naught, if the input is 0, Q naught, if the input is 0, we will move to the state Q1. So this transition function actually is represented like this. And what is this? This is the output. Actually, the intersection point of Q0 to Q1 represents the output. So the transition function, again, I write it again, the delta Q0. And if we are having input 0, then the output would be Q1. So similarly, all the rows indicate the same thing. So for every state, we have to determine the input symbol and what might be the next state. So the next states are at the intersection of state and the input symbol. So these actually are the outputs. These on the intersection of Q0, Q0, and Q0, Q1, we have like Q2, and Q2, 1, we have intersection like this Q2. So this table actually graphical or tabular representation of the transition function. I hope you have understand today's topic, and we will discuss some more example in the next lecture. Thank you very much for listening and understanding the concepts.